Welcome, math enthusiast. I am Carlo. Alright, let's kick things off with our first topic, approximating areas under the curve. So let's illustrate this with an example. Considering the function x squared plus 1 over the interval from 0 to 2. Our goal is to approximate the area under the curve using rectangles. So we will use two rectangles to approximate the area. We will divide the intervals 0 and 2 into two equal subintervals. Let's use the given values. N is equal to the number of rectangles, while A and B is the interval which is 0 and 2 respectively. And by substituting this in the formula delta x is equal to b minus a all over n, we can say that delta x is equal to 1. So let's find the area of the rectangles on the left side. We can identify if we are finding the left side since the upper left corner of the rectangles are the one touching the lines and also upper right corner for the right sided. So by using the formula which is summation of f of x times delta x, we can say that the area of the left side is 3 while on the right side is 7. And of course, if we increase the number of rectangles, approximation would be better. Now let's talk about finding the net area shown on a graph. If you're figuring out the net area from point A to point B on a graph, you're essentially finding the total area between the function and the x-axis within that range. This means that adding up all the areas above the x-axis which is considered as positive and subtracting the areas below which is considered as negative. For example, take the function negative x squared plus 3x. The shaded region on the graph represent the area between the curve and the x-axis. Any area above the x-axis counts as positive, and any below counts as negative. If the positive areas have a total of 4, which is 3 and 1, while the negative area has a total of 7, then the net area from A to B is found by adding the positive areas and subtracting the negative, resulting in a net area of negative 3. This net area represents the difference between the positive and negative areas.
Hello everyone, Justin here. As Carlos said earlier, that if we increase the number of rectangles, the approximation will be better. And that exactly is what we're going to do. This is Riemann sums in a regular partitioning, graph visualization, and table. Let us just borrow his sample function from earlier, x squared plus 1. Here, the curve's area is estimated using two subintervals, giving us a left-sided rectangle approximation of 3 and the right-sided rectangle approximation of 7. Let us use the midpoint rule with the simple formula by which obtaining the mean of left Riemann sum and right Riemann sum, which gives us the approximation of 5. This approximation is more on point as it compensates the empty area of the curve with the excess outside the curve. Let's set aside this two subinterval approximation and let us approximate by dividing the subintervals into 4 and 8 respectively. First, by dividing the subintervals, we also have to figure out the width of every subintervals with the formula used earlier by Carlo, where n is the number of our rectangle, subintervals or our partition, and delta x is the width of our rectangles. By plugging our numbers in, we get 1 half as our delta x. After this, using the formula used by Carlo earlier again, we get the left Riemann sum of 3.75 and the right Riemann sum of 5.75. Using our midpoint rule, we get the mean of 4.75, and we do the same process under the 8 subintervals, which will give us the mean of 4.68. Now, how can we say that by increasing the subintervals, we get much accurate approximation? Let us visualize it further. Rectangles are used in calculation since, as we all know, finding an area of a rectangle only requires its width and height. But since the corners of rectangle are sharp and angular, they cannot fully encompass or smoothly follow the curves of a shape or function. We introduces the Riemann sums, which divides the rectangles into subintervals, giving us accurate approximation on the area of a curve. What we did earlier was a regular partitioning, as we have equal delta x for all of our partitions. Irregular partitioning have a different width in every rectangle. One way we are going to encounter irregular partitioning is with the use of tables. Tables can have points in x and f of x, which we have to directly illustrate our rectangle and solve its area respectively until we get its overall area. Tables are not used in functions as functions are very stable with equal subintervals.